For today's discussion, we will work on some equations which involve exponentials and logarithms. And in the process, we will be able to recall properties of exponentials and logarithms, as well as how to solve equations which involves these two um, operators. Okay, so let's start with our first problem. So we want to solve the following equation. 10 raised to 2x equals 100,000. So before we solve this, let us recall these properties. So properties of exponents, we have one is you have a to the 0. This is equal to 1. Okay. And then we have a to the m times a to the n. This is equal to a to the m plus n. Okay. And then we also have a to the m times or raised to n. This is equal to a raised to m times n. Okay. And of course, if you have something like product of two exponential expressions with the same power. So for example, you have a to the m, b to the m. This is equal to the product ab, and then you raise it to power m. Okay? And then you also have a over b raised to m. You can write this as a to the m over b to the m. Okay, so I apologize for the inconsistency in these two bullets here, but anyway, in here we just distributed the power m on the product AB. And similarly here, we just distributed the power m on the quotient A over B. Okay, and I forgot to mention in this part, if you have something like a to the m divided by a to the n, then this is equal to a to the m minus n. Okay, now in terms of equality, we need to recall the following. So if you have a to the m equals a to the n, then their powers, okay, must also be equal. Okay, so if a to the m equals a to the n, then m must be equal to n. And this particular property we are going to use in order to solve this equation. Now, first tip. If you have exponential expressions on one side of the equation, you look at the base of your power or your exponents, okay, or exponential expression. So for example, here you have base 10. And then on the other side of the equation, there's only constant, okay? Then the first thing that you can do is think of a way to write the constant in terms of a power with the same base. So for example, this 100,000 here, we try to write this as a power of 10. Okay? And we know that this 100,000, okay, this 100,000, you can write this as 10 raised to power 5. Okay? So you have 10 times 10, that's 100. So that's 10 squared. And then 100 times 100, that's 10,000. But that's 10 squared times 10 squared. And 10 squared times 10 squared, that's 10 to the 4. And then you multiply again by 10, that becomes 10 to the 5. And 10,000 times 10, that's equal to 100,000. Okay? So this 100,000 can be written as 10 to the 5. Now, using this property here. You have 10 raised to 2x equals 10 to the 5. This means that 2x must be equal to 5. Correct? So if a to the m equals a to the n, then m must be equal to n. So 2x must be equal to 5. And therefore, we have x equals 5 over 2. So this is the solution to this equation. Okay? So question on this first problem. Next problem, we want to solve the following equation. 5 raised to 2x minus 1 equals 625. So again, on the left-hand side, we have an exponential expression with base 5. And then on the right-hand side, we have a constant. It's 625, and it seems that this 625 can be divided by 5. And if we divide this by 5, there's a possibility that it can be still divided by 5, and so on and so forth. Okay? Which means that there's a possibility that this 625 is a power of 5. Now, one way to check whether the constant is a power of your desired base, okay? In particular here, we have base 5. So one way is to continuously divide that constant with that base. Okay? So what I'm saying is we start with 625, and then you divide this by 5. Okay? Let me write it this way. Let me write it this way. So you divide this by 5. And you know, 625 divided by 5, what is this? You have 6 divided by 5, that's 1. And then you have here 5. Okay? So what do we get? You have here 125. Try to check. Okay? Anyway, let's rewrite this in another form. I'm not used to working on this kind of division. So let me do it my usual way. But you will get that 125. So in here, 6 divided by 5, that's 1. And then 1 times 5, that's 5. And then 6 minus 5, that's 1. Bring down 2. Okay? And then you have 12 divided by 5, that's 2. 2 times 5, that's 10. 10 minus 12. 12 minus 10, that's 2. And then you bring down 5. Okay? And then here you have 25 divided by 5, you have 5. Then 5 times 5, that's 25. Okay? And this is equal to 0. Okay? So this means that your 625, this is equal to 5 times 125. And as you can see, again, this is 125 and it's divisible further by 5. Okay? So from there, you have 125. You divide this by 5. What you will get here is 25. But let us proceed with the long division. So 2 times 5, you start with the 2. You start with this 12 here. So 12 divided by 5, this is equal to 2. And then 2 times 5, that's 10. And then you have 12 minus 10, that's 2. Bring down 5. You have 25 divided by 5, that's again 5. And then you have 25 in here, and that's 0. Meaning, here you have 5 times your 25. It's now 5 times 25. And we easily get that 25 is actually 5 times 5, which means that the 625 is 5 to the 4. Okay? 5 raised to power 4. Now, this solution, I don't know how you do your long division back in the day, but this is our method, okay? So you can do the same method if you are familiar with this, but if you have a different method in your long division, try to work on that. But again, our purpose is you start with your right-hand side or your constant, you continuously divide it by the base, the desired base, until you reach some power of your base. Okay? There's a possibility that the constant on the right-hand side is not actually a power of your desired base, which means that you cannot do anything with that. Meaning you cannot write it as a power of this desired base, and therefore you have to use another method in solving the equation. And I will present, of course, that method later in the discussion. Okay? But let us continue with this equation. So we now know that 625 is 5 raised to 4. So we write now 625 as 5 raised to 4. And then using this same property here, okay, we just equate the exponent. You have 2x minus 1 equals, so 2x minus 1 equals 4. And then, of course, we solve for x, okay? This means that we have 2x equals 5, which means that x is equal to 5 over 2. So this is the solution to this equation. Okay? So question. All right. Let's work on our next problem. So here you have to solve for x in the equation 7 raised to x squared minus 1 equals 343. Okay? So for this, let's do the method that I used in the previous example. We have 343. We divide this by 7. So, of course, 3 is not divisible by 7. 34 is divisible by 7. Not divisible by 7, but at least 34 is greater than 7. So we can divide. 34 divided by 7, that's equal to 4. And then 4 times 7, that's 28. And then we have 34 minus 28, that's 6. Okay? And then you bring down 3. And then we now have 63 divided by 7. This is 9. And 9 times 7, this is 63. And this is equal to 0. Which means that your 343, this is equal to 7 times 49. And I hope you easily know that 49 is 7 times 7. So this is equal to 7 times 7 times 7, or we now write this as 7 raised to power 3. Okay? Which means we now write this 343 as 7 raised to power 3. Okay? And then as in before, we just equate the exponents. X squared minus 1, okay, must be equal to 3. And therefore, what do we get? We have x squared equals 4. And therefore, our x is equal to plus or minus square root of 4 But square root of 4, that's equal to 2. So our x is plus or minus 2. So these are the solutions to this equation in here. Okay? Question so far?
Sir,
Yep, go ahead.
what if we don't put plus or minus? Like we just leave it square root of?
Then you will just give one of the two solutions. Take note, this will have two solutions. So
So,
if you only put, for example, square root of 4, which is equal to 2, then you just gave me the principal square root. But negative 2 is also a solution to this equation. So you missed one of them.
okay. Thank you.
All right, you're welcome. Other questions? Now let's work on this. So solve the following equation. 1 over 9 raised to 3 to the x, 1 over 9 raised to 3x equals 27x squared. Okay? So at first sight, it looks like 1 over 9 and 27 uh, is or do not have the same base. Okay? I mean, you cannot write directly 1 over 9 as a power of 27 or 27 as a power of 1 over 9. Okay? So for this kind of problems, what you do is to try to write each base. So for example, in here, you have 1 over 9 as the base of this expression here, and here, 27 is the base of this expression. So try to write each base as a power of another base and check if that base works also for the other expression. Okay? Meaning, try to write the two bases here as a power of a common base. And we can actually do that in this base 1 over 9 and 27. Okay? Take note. First, 1 over 9. Note that 9 is equal to 3 squared. So 1 over 9 is equal to 1 over 3 squared. Or you can now write this as 3 raised to negative 1. On the other hand, 27, I hope this is easy. Okay? 27, this is uh, 3 raised to power 3. So 3 times 3, that's 9. Times 3 again, that's 27. So 1 over 9 and 27 are both a power of 3. So we use this, okay? We use this and replace respectively 1 over 9 and 27 in order to have an equation with a common base. So using this means that we write 1 over 9 as 3 raised to negative 1, but this has exponent 3x. And then on the other side, you have 27, but that's 3 to the 3, and it has exponent x squared. So if we simplify this, we use properties of exponents. Okay? We just multiply the exponents. So negative 1 times 3x. So that becomes 3 raised to negative 3x. And on the other side, you have 3 raised to 3 raised to x squared. So 3 times x squared, you have 3 raised to 3x squared. So now we have a common base. Okay? So we can now equate the exponents. So this means that we have minus 3x. Sorry, this should have been 3 raised to negative 2, not negative 1. Okay? So let me edit that. So 3 raised to negative 2. So this guy here must also be negative 2. Okay? And therefore, this guy here must be negative 6x. Okay? Sorry about that. But let us continue. We have negative 6x equals. Um, so it just reacted. So again, I replace the negative 1 here with negative 2 here, negative 2. Okay, so negative 2 times 3x, that's minus 6x. So equating the exponents, we have negative 6x equals 3x squared. Okay, so now we solve this equation. We solve this equation. Let us write this in standard form, meaning we write this as 3x squared plus 6x equals 0. So I put this on the other side. So it becomes 3x squared plus 6x, and then on this side will be 0. And then I interchange that. And then from here, we factor out 3x. So to solve for the values of x, or to solve for the solution, we can factor 3x. And then what remains inside is x plus 2. And this is equal to 0. And therefore, this means that your x must be equal to 0, or your x plus 2 equals 0. Or this means that your x equals 0, or your x equals minus 2. Okay? So from here, you have x equals 0 or x plus 2 equals 0. And therefore, solving for x, particularly in this, your x is equal to negative 2. And of course, your x is equal 0 is there. So these are the solutions to the equation. Now, some students will do this. Okay, some students will do this. For example, from this part, okay, from this part, what they're going to do is to divide the equation by, or divide each side of the equation by 3x. Okay? So when they do that, okay, when they do that, they will get minus 2 equals x. Okay? So how did that happen? So let me write that more completely. So you have minus 6x and then equals x squared. They divide it, sorry, 3x squared. They divide it by 3x, divide this by 3x, and that's where they will get minus 2 equals x, or x equals minus 2. And then they will box this as their final answer. So what happened? They will miss this x equals 0 as a solution. Okay? Take note. Take note that when you divide by 3x, take note that your divisor has a variable. And this means when you do this, you assume that the expression you are using as a divisor is not equal to 0. Meaning, when you do this, you are assuming that your x is not equal to 0. Because of course, if x equals 0, then this cannot be done. So when you do this, you are assuming this case. you are adding a condition. But then again, after getting this, what about the case when x equals 0? Okay? So again, when you do something like this, you are adding a condition. And particularly for this, the condition is that your x must not be equal to 0. But the question is, after doing this, what about the case when x equals 0? Of course, when x equals 0, this equation will still be true. 0 equals 0. Then you have the validity of the equation when x equals 0. So a lot of students do this. Okay? A lot of students do this. And therefore, they are missing some of the solutions. This is totally fine if you do this, but then again, you will get some deduction if you missed out the other solution. Okay? That's why when you have something like this, your first instinct is try to write it in standard form. So you will not lose some solutions, that's one, or you don't need to add conditions. Okay? Of course, there are other students who do this, okay? But then they will continue with that if x equals 0, if x equals 0, we will have 0 equals 0. So x equals 0 is also a solution. And that's totally fine. At least they knew that x equals 0 can be a solution to this equation. Okay? Question? Question or clarification? Okay. So let's have our next problem here. So we have 32 raised to x squared minus 3 equals 1/4 raised to 2x squared plus 5. Okay? So again, this is very similar to the last problem. We cannot write 32 as a power of 1/4. And conversely, we cannot write 1/4 as a power of 32. However, both of them, 32 and 1/4, can be written as powers of a common base. And we easily see what base that would be. 1/4 is just 1 over 2 squared. And 1 over 2 squared, you can write it as 2 raised to negative 2. Okay? So 1/4 here. So, okay. 1/4, it's written as 1 over 2 raised to power 2. And 1 over 2 raised to power 2 can be written as 2 raised to power negative 2. So we expect that 32 can be written as a power of 2. Okay? And we know that at least 32, that's equal to 8 times 4. And we easily know that 8, it's 2 to the power 3. And then your 4, it's 2 to the power 2, which means that 32 is 2 to the power 5. Okay? So again, we substitute this 2 to the power negative 2 for 1/4 and 2 to the power 5 for 32, so that our equation becomes, so 2 to the power 5 quantity raised to x squared minus 3. Okay? And then this is equal to 2 to the power negative 2. And then we raise this to 2x squared uh, plus 5. Okay? And then we apply again laws of exponents here. Okay? This will give us 2 to the power 5x squared minus 15. And then on the right-hand side, we will have 2 raised to minus 4x squared minus 10. And then now we have the same base. We use the property that we recalled earlier. So we just equate exponents. 5x squared minus 15. And then this must be equal to minus 4x squared minus 10. So we solve for x. We bring this minus 4x squared on this side, on the left-hand side, and then minus 15, we bring it to the right-hand side. So we have 5x squared plus 4x squared equals minus 10 plus 15. And in here, on the left-hand side, we have 9x squared. On the right-hand side, we have 5. So we solve for x. We can divide by 9 so that we will have x squared equals 5 over 9. And then we take the square root. So this becomes x equals plus or minus square root of 5 over 9. But we know square root of 9, that's 3. So we can rewrite this as x equals plus or minus square root of 5 over 3. So these are the two solutions to this equation in here. Okay. Question for this problem? Now, let us recall some properties for logarithms. Okay. So here, we want to evaluate logarithm of 81 base 3 without using a calculator. Okay. So this means this should be done, or this expression here can be done using properties of logarithms, so that we will not need uh, a calculator. So what properties do we need to recall? Well, first, this is one of the nice properties. Log 1 of any base, this is equal to 0. Okay? So logarithm of 1 with any base a, this is always equal to 0. Okay? We also recall log of a with base a. this is equal to 1. And then we also recall log of a to the r with base a, okay? Log of a to the r with base a. So in here, it seems like a and the base a here. So base for the exponent, a to the r, and then the base of the logarithm, if they are the same, it seems like they will be cancelled. So this is just equal to r. Okay? So I'll stop the recall at this part because this guy here is the one we need in order to solve for the exact value of log of 81 base 3. So we have a base 3. We expect that this 81 can be written as a power of 3. And indeed, it is. Okay? 81, this is equal to 9 times 9. Okay? But 9, we know it's 3 squared. So this is just 3 squared times 3 squared. And therefore, this is 3 to the 4. Which means log 81 base 3 can be written as log of 3 to the 4 base 3. And now we use this property. This is simply equal to 4. Okay? So, if you find this kind of problem, okay, you are asked to solve logarithm, the exact value of logarithms without using a calculator, most probably this is the property you will need. And therefore, what you need to do is to look for the base of the logarithm and then write the argument as a power of that base. So in here, we have base 3. The argument is 81. We write 81 as a power of 3. And therefore, this property here can be used. Okay? Let's look at this example again. Another example here. So, you have log base a, and then you have 1 over a to the 7. So, let's answer this in two ways. Okay? The first way, we rewrite 1 over a to the 7. Okay? We rewrite 1 over a to the 7 as a raised to negative 7. Okay? And therefore, we compute the logarithm of a raised to negative 7 with base a. So using the property earlier, in the previous slide, this is simply negative 7. So this exponent here. Okay? Now, let us solve this using a different um, method. So I would be able to recall a certain properties of logarithms. So remember, log of BC with base A, this is equal to log of B with base A plus log of C with base A. Okay? And another property, if we have log of B over C with base A, this is equal to log of B with base A minus log of C with base A. So this particular property we use now in order to solve log of 1 over a to the 7 with base A. Okay? So with this direction, log of 1 over a to the 7 with base a. We now write this as log of 1 with base a minus log of a to the 7 with base a. And in the previous slide, I recalled that log 1 with any base, this guy here, is just equal to 0. So we'll just have 0, and then minus, and then in here, 7 will just go down. So 0 minus 7. And indeed, this is equal to negative 7, just like in the previous solution. Okay? So you may use this property here, property of exponent, or you can use this property of logarithms. Okay? Next problem here. We want to compute for log of 2 base 1/2 without using a calculator. So we now have a base 1/2. Our argument is 2. But you know that 2 can be written as 1 over 2 raised to negative 1. So that this log of 2 base 1/2 is just log of 1 over 2 raised to negative 1 base 1/2. But this guy here can be rewritten as quantity 1/2 raised to negative 1. So this guy here is now equal to log of 1/2 raised to negative 1 base 1/2. Which means this is simply negative 1. Okay? Question. Next problem here, we have log of 8 over 27 base 2/3. So similar to the previous problem, but in here, our base is 2/3, so we expect that 8 over 27 can be written as a power of 2/3. So try to check that 8 over 27 is actually 2/3 raised to power 3. So this guy here, it's equal to log of 2 over 3 raised to the power 3 with base 2 over 3. Which means that this guy here, this is equal to 3. Okay? Question. So again, if you are asked to find the exact value of logarithms without using a calculator, this is the solution. Okay, this is the solution. And when we ask you to do this, we expect that you will write the solution. If you only wrote the final answer, then you will get nothing, because technically that final answer was obtained, or we will think that that final answer was obtained using a calculator. Okay? Now, let's look at these problems. So this time, equations involving logarithms. So in here, what we need to recall is the following. Y equals logarithm of x with base a. Okay? So y, logarithm of x with base a. This is equivalent to a to the y equals x. Okay? So a to the y equals x. So the base of the logarithm, it's also the base of the exponential expression when converted to exponential expression. Okay? We also need to recall the following. So later we might need this, the logarithm with base 10. This is equivalent, or this is written simply as log. Okay? So if our base is 10, then we remove that base. Or if you don't see a subscript for the log, then the base must be equal to 10. Also, we have logarithm with base e. Okay? We simply write this as ln. Okay? So we might need these two later in the next slides. But anyway, for this equation here, we will only use this first part for now. Okay? So this guy, log of x base 16 equals 1/2, can now be written as x equals 16 raised to 1/2. But 16 raised to 1/2, it's just equal to 4. Okay? So x equals 4. So this is the solution to this equation. Question? Next problem. We want to find log of square root of 3 with base x. Take note of that. With base x equals negative 1/2. So we want to solve for the value of x, satisfying log square root of 3 base x equals negative 1/2. So again, we just use the property or the definition of logarithm. So this guy here, it's equivalent. So this guy here, it's equivalent to square root of 3 equals x raised to negative 1/2. Okay? So, one way of solving this, we raise this guy here to power negative 2. Okay? And therefore, this guy here will also be raised to power negative 2. So, if your x raised to negative 1/2 is raised to power negative 2, okay? If your x raised to negative 1/2 is raised to power negative 2, if you multiply negative 1/2 and negative 2, it will give you positive 1. Okay? So that's the right-hand side. Left-hand side here, square root of 3 raised to power negative 2. Which means, for this guy, this will be 1 over square root of 3 squared. And then for this guy here, negative 1/2 times negative 2, that's positive 1. So question, why is it negative 2? Because I know that if I multiply negative 2 to negative 1/2, it will give me positive 1. And therefore, I'll only get x. Okay? So basically, you raise this guy here to the reciprocal of the power. Okay? So you raise this guy here to the reciprocal of the current power of x. Okay? So simplifying this, so your x raised to 1, it's simply x. But for this, you have 1 over square root of x squared. That's equal to 1 over 3. So this is our final answer. Okay? So this is one way to do it. Some students will do this, and this is totally fine. Okay? So for example, you have now square root of 3 equals 1 over x raised to 1 half. So you put this guy here in the denominator, so the exponent will become positive. And then you can solve for x. You can just cross multiply this. Okay? This will give you x raised to 1 half equals 1 over square root of 3. And then, of course, that exponent 1 half, you raise this guy here to power 2. You square it. So that 1 half will cancel the power 2. Okay? Which gives us x. So raised to 1 half raised to power 2. This is 1 over square root of 3 raised to power 2. And you will still get the same answer. X equals 1 over 3. Okay? So it's the same thing. Question. Next problem here, you have log of 1 over 10 to the x equals 5. So remember, if there's no subscript, the base is automatically 10. So we just rewrite this 1 over 10 to the x as 10 raised to negative x. So the left-hand side becomes log of 10 raised to negative x. The right-hand side, it's still 5. But again, this is base 10. And you now have here 10 raised to negative x. So the left-hand side will just be negative x. The right-hand side, it's still 5. And therefore, the x must be equal to negative 5. Okay? Question. Next problem here. So we have ln of e raised to 2x plus 7 equals negative 8. And recall, ln, it's log base e. So log base e of e raised to 2x plus 7 equals negative 8. So the ln and the e, they will just cancel each other's operation. And therefore, you will have 2x plus 7. And this one here is equal to negative 8. So we solve for x. This is equal to 2x equals minus 8 minus 7, or we have 2x equals minus 15. And therefore, x is equal to minus 15 divided by 2. So this is our solution. question. Next problem. 10 raised to x plus 1 equals 2. So we go back to exponential equation, but this time, unlike in the previous set of equations that we need to solve, in here, observe that your 10 cannot be written as a power of 2 and vice versa. 2 cannot be written as a power of 10. And furthermore, we cannot find common base to both of them. Okay? Which means we will use another way to solve this equation. Particularly, we use logarithms. Okay? So, when you have this kind of equation, okay, you look for the expression with exponent variables. So in this side, on the left-hand side, you have 10 raised to x plus 1. On the right-hand side, you just have constant, and which is good. Once you identify the expression with exponent variable, if there's only one of that, okay, you get the log of both sides of the equation and use the base of your exponential expression. Okay? So what I'm saying is, you have here 10 to the x plus 1. Our base is 10. Of course, on the right-hand side, we just have the constant. So, we will use logarithm with base 10. Okay? So, what we're going to do is to take the log of both sides of the equation with base 10. So, in here, we get the log base 10 of both sides of the equation. So, log base 10 of 10 to the x plus 1. This is equal to log base 10 of 2. Okay? Take note, let us recall that property. So log of b with base a equals log of c with base a. This is, we can show that b is equal to c. And conversely, if you have two equal numbers, their logarithm with the same base equals. So that's what we used in here. This guy here equals 2. So if we take the log of both sides of the equation using the same base, then there must be equal. They must be equal. Okay? But in here, what's the point of using base 10? We have an exponential expression here with base 10. If we use base 10 to log, we know that this 10 here or this 10 here, they will just cancel each other. Which means that on the left-hand side, this is just x plus 1. Okay? Again, let me pull out that property again. Log base a of a, sorry, log of a to the r base a, this is equal to r. So this is the one we used in here. Okay? This subscript 10 here is just for emphasis. Okay? If you remove that base, it's still base 10. So anyway, left-hand side, it's just x plus 1. For the right-hand side, this is just log 2. So again, now I am removing that base 10. Okay? I'm removing the subscript. This is still log base 10. So solving for x, we have x equals negative 1 plus log 2. So this is the final answer. Okay? Question. Now, warning. Some students will do this. Okay? So from here, they will write the solution as x equals log 2 minus 1. And this is totally fine. If you wrote your solution to be like this. However, there are students, okay, there are students who will do this. Oh, there's a 2 minus 1. So your x equals log of 2 minus 1, which is 1. Oh, we have log 1 here, so x must be equal to 0. So this part here, this is now incorrect. Take note that in here we just have log 2. And then we subtract 1 from logarithm of 2. This is not log of 2 minus 1. Okay? This is log 2 minus 1. Okay? And I'm telling you because um, many students do this. So I hope you will not do this. So it's
I just
better.
have one question, if that's okay.
Yep. Yep.
Okay, so in the second step there, where like the base 10 canceled there, the log 10, so you went to x plus 1 equals log 2.
Mm-hmm.
What's the rule about like the log 10 canceling on the other side of the equation?
No,
Other side of the equation.
this is what we have here. Log of 10, we simply write it as log. It's just annotation.
Okay.
There's no cancellation done in this side. It's just that
Okay.
we when we have base 10, we simply write log. They mean the same thing.
Okay.
Okay? Yeah. Other questions? Another thing, you can use other base. It's totally fine. You can use log base your favorite number. But make sure you do that on the same side. Say log base 9, you also use log base 9 on the other side. However, you will not be able to use this property. Okay? Which means the log base 9 will be there. Particularly, log of 10 base 9 will be there. Okay? So take note of this. If you have the same base here, it seems that they will just cancel each other. If your argument is not the same as the base, for example, here you have log b to the r base a. This is r log of b base a. So you still have that log b base a. So if you use a different base, you will have that log 10 of your chosen base. Okay? So that's why my tip was, you look at the equation, you check the exponential expression if it exists, and then you use the base of that exponential expression as the base of your logarithm. Okay? However, if you have one or two or three exponential expressions and they have different bases, then just choose one. And we cannot, you cannot simplify it, all of them. I mean, the exponential expressions, you cannot simplify it this way. Definitely, this part here will appear. Okay? Okay, so let's look at this. So solve the equation, e to the 2x minus 3 equals 4. So in here, we have base E, okay? And we have constant 4 on the other side. So your 4 cannot be written in terms as a power of E, or your E cannot be written as a power of 4, okay? So we use a different solution, particularly the solution that we used in the previous example. And in here, we have base E, so we use ln. Okay, so remember, already I have recalled this. Your ln, it's logarithm with base E. So we use ln. So we have ln of E to the 2x minus 3. This must be equal to ln of 4. And same property that we used in the previous problem. It's like your ln and your E here cancel, so that we'll just have 2x minus 3 on the left-hand side. And on the right-hand side, we have ln of 4. And then we solve for x. So in here, you have 2x equals 3 plus ln of 4. Your x is now equal to 3 plus ln of 4 divided by 2. I will accept this as a final answer. Okay? But some students will do this. So from here, you have ln of 4. You know that 4 is 2 squared. Okay? So let us continue from there. So x equals 3 plus ln of 2 to the power 2 all over 2. And then you have now 2 to the power 2. So this exponent 2 will go down as a coefficient of your log. So x equals 3 plus 2 ln of 2 divided by 2. And therefore, some students will write this 3 over 2 plus ln of 2. And this is also correct. Okay? This is totally fine. Question? Now, some students, however, will also do this. Okay? Say you have x equals, so I'll write from here, x equals 3 plus 2 ln of 2 over 2. Oops, I found that 2, I can cancel this, and they will write this, 3 plus ln of 2. Now this is wrong, okay? Okay? You cannot do this cancellation. It's like what you are doing is something like this, which I found in some of the solutions of your classmates in their midterm exam. We had their x squared plus 1 over x squared minus 1. And then they just cancel the x squared. Oh, there's an x squared and x squared there. Cancel, cancel. This is equal to negative 1. Okay? So this is a big no-no. Okay? Let me erase those thick x's there. So again, this guy here, it's a big no-no. You cannot do this. You cannot cancel that because this is one expression, x squared plus 1. This is also one expression, x squared minus 1. they are not factored form. They are not products. So please do not do this again if you are that person. Okay? Another no-no here. Some students will do this. ln say 6 divided by 2, and oh, 6 is equal to 3 times 2. So they will write this ln of 3 times 2, 3 times 2 divided by 2, and now we cancel the 2 there, so we'll just have ln of 3. Again, this is not correct. ln of 6 over 2, it's just ln of 6 over 2. Okay? Do not factor 6 into 3 times 2 and then you cancel those 2. It's not allowed. Take note that in here, although your 4 can be written as 2 times 2, okay? That is not the reason why the 2 canceled. Okay? Some students will think of this part here as 3 plus ln of 2 times 2 over 2. They will cancel the 2 here, and they will write 3 over 2 plus ln of 2. They are correct in a sense. The 2 was only canceled on this part, so that 2 must remain with the 3 there. Okay? And take note, you got the correct answer for a wrong solution. So even though you have the correct answer, you will still get deduction because you applied as something that is not valid. Is that clear? So this part here, this guy here, it's wrong. Although you got the correct answer here. Question. Next problem here. We want to solve the equation 2 to the 3x plus 2 equals 1/3. Okay? So we have base 2 here, and then we have constant 1/3. So we look at this expression, and then since we have base 2 in the exponential expression, we use 2 as the base of our logarithm. So we get the logarithm base 2 of both sides of the equation. So you have log base 2 of 2 raised to 3x plus 2. This is equal to log base 2 of 1 over 3. And then in this part here, left-hand side now can be written as 3x plus 2. And of course, you can simplify this if you want. But let us just write this as is. So log of 1/3 base 2. Then we solve for x. We have 3x. And as in before, I will write the 2 before the log. So we have minus 2 plus log 1/3 base 2. And finally, x, this is equal to minus 2 plus log of 1/3 base divided by 3. Okay? And this is our final answer. Oops, I forgot to write base 2 there. Now, this is the final correct answer. Okay? Question. So again, in this problem and in the previous problems, we use the base of the exponential expression that we have as the base of the logarithm. But as I have said, you can use other bases. You can use any other base. But don't forget that you will have the log of base. For example, in this equation, we use base 3 instead. You will have log of 2 base 3 somewhere in your solution or in your final answer. Let me do that just for an illustration. So instead of using base 2, say I use log base 3. So I have here log base 3 of 2 raised to 3x plus 2. This is equal to log base 3 of 1/3. Okay? This guy here we can simplify. So on the left-hand side, we can bring down 3x plus 2 times log of 2 base 3. That's the left-hand side. Whereas the right-hand side, let us rewrite 1/3 as 3 raised to negative 1. And we have base 3. So 1/3, that's the same as 3 raised to negative 1. So the right-hand side here, we can bring down negative 1. So you have 3x plus 2 log 2 base 3 equals negative 1. Again, we can do this right-hand side here because we use base 3. If you use other base, say base 4, base 5, etc., you will not get this right-hand side negative 1. You will have that log base something, just like what happened here in your left-hand side. So from here, we just solve for x. You have 3x plus 2. This is equal to negative 1 over log 2 base 3. And then we continue solving for x. You have 3x equals minus 2 minus 1 over log of 2 base 3. Okay? And then finally, your x, this is equal to negative 2 minus 1 over log 2 base 3 all over 3. Okay? So let me just centralize this. You have x equals this guy here. And this is your final answer. Okay? So again, you can use other base, and you will get a final answer which is equal to this original answer I wrote. Question? So this will be my last example, and I want you to work on the examples or the problems on pages 75 to 76 of the 016 module. So the problems that I solved today are from these pages also. Okay? They're also from these pages. So thank you for staying, and I hope you were able to practice the concept. And bye-bye.